All right, welcome to the last video of section 2.4, but not the least. This is one of the most useful theorems we are going to learn in the whole class. We're going to be using this theorem pretty much throughout the rest of the class. And it's so useful because there's so many things you can do with it. So first, let's read it. It says if A is a C by C matrix, meaning square, the same number of rows as columns, then the following are equivalent. And notice this does not apply to rectangles with more rows than columns or more columns than rows. So when we say the following are equivalent, we mean if you know that one of these things is true, then all the other ones are going to be true as well. And that also means if one of them is false, the rest of them are going to be false as well. So, for example, if you figure out that you have a matrix with linearly independent columns, that's got to be an invertible matrix. If you find out that, you can find a particular y vector that makes it so ax equals y doesn't have a solution, so in other words, it is not the case that for every y in RC, ax equals y has a solution, then that means everything else is also false. That means it's not invertible. That means there doesn't even exist a matrix you can multiply on one side by A to get the identity. So yeah, it's a really powerful theorem. We're going to use it a lot, and we're going to prove it here. So this picture here is like a map of the proof. And some of these things, like the fact that some of these things are equivalent, is really easy. And we'll prove those first. But maybe we should understand what this picture is. Like if there's an arrow from like 1 to 2, that means we're going to make an argument that if thing 1 is true, if A is invertible, then there exists a matrix P such that PA is equal to the identity. Actually, that one is so obvious that we can just explain that one right now. So if A is invertible, that means A inverse exists. And the definition of A inverse means you can multiply it by A and get the identity. Like so. I'm going to write a little argument here for why that is. So yeah, A inverse could be your P. We're going to argue all of these things. So some of them are really easy like that one. Some of them are not so easy. But before we dive into it, I want to point out that the first 3 things here are about matrix multiplication. And everything after that, numbers 4 through 9, are all about stuff from chapter 1. Linear independence, pivot positions, the existence and uniqueness of solutions. So I think we should actually prove these ones first, and then we'll see how that's all connected to the stuff about invertibility. So let's look at a quick one. Let's say we want to show why thing 6 is equivalent to thing 7. This is actually pretty straightforward because it's just the definition of linear independence. And if that's not obvious to you that these 2 things are saying the same thing, this is actually a good place to review previous sections because these ideas keep coming back. So I'll try to give you some notes at where you could go back to read or watch an old video if you need to. A lot of this was done in 1.4. So for example, at the beginning of 1.4, we have the definition of linear independence. We say a list is linear independence if the only solution of this system of equations is the trivial solution. And the solution set of this we also call the null space. So it's kind of just a change of notation. So those are equivalent by definition. Let's also look at these two things, 8 and 9. Why are these equivalent? Well, the column space is the set of vectors that can be written as ax for some x in RC. So if every y can be written a times x, then that means the column space is all of RC. So that's again just a change of notation. And we also went over that in 1.4. Also, the column space as written in the form of things that you can write as a times x, that was also 2.1, where we defined matrix by vector multiplication. So yeah, you can find information about that in sections 1.4 and 2.1. All right, let's see what else do we have. Maybe we can start connecting things to 5. 5 says that A has C pivot positions, and C is the same as the number of rows and columns. And we remember from 1.2 that, like, if A has C pivot positions, let's say A is like 4 by 4, then when you get the reduced echelon form of A, like, you can only have one pivot per row because the leading entry has to be the leftmost non-zero entry. So you must have a pivot in every row. And if you have 4 pivots, you can't have 2 pivots in the same column because of the definition of echelon form. They have to make the staircase shape. Each one has to be to the right of the one above it. So you can't have more than one in a column either. So the only place these pivot positions can fit is on the main diagonal. And that means that the reduced echelon form of A must be the identity matrix. So that actually explains why these two things are equivalent, 4 and 5. And if that argument doesn't make sense to you, go back and review section 1.2. Be a good place to catch up on that. Now, if A has C pivot positions, like we said, it must have a pivot in every row and in every column. So that means that A has a pivot in every row. And let's actually go back to 1.4. That is equivalent to every system of equations that has A as its coefficient matrix is consistent. And a system that has A as its coefficient matrix is a system that would be written as AX equals Y. And the span of the columns, that's another way of saying the column space of A equals all of R. In this case, it's RR because, well, R and C are the same. So we could say RC. Now, if you're not sure about, like, why are these things the same, it might help to go look at where we defined what A times X means. That was in 2.1. There's another version of the existence theorem here that makes that more explicit, that if A has a pivot position in every row, then every system of equations that has A as its coefficient matrix is consistent, which we can now write like this. So those are all equivalent. So that connects 5 with 8, this always being consistent. So yeah, having a pivot in every row means this is always consistent, but how do you know it's unique? That's what thing 6 says. And let's look at the uniqueness theorem. Oh, here's a convenient version of the uniqueness theorem. Now, these are all equivalent, A having a pivot position in every column, the null space being the set that just has 0 in it, which again means the same thing as having a linearly independent list of vectors. So yeah, again, section 1.4 and 2.1 go into that. At this point, we have connected all of things 4 through 9. And again, this is basically a combination of the existence and uniqueness theorems, because if it's a square matrix, then having a pivot in every row is equivalent to having a pivot in every column. So the existence and uniqueness theorem get mashed together into this mess. Now, how does that connect to the stuff about inverses or partial inverses? Let's see. First of all, the fact that thing 1 implies things 2 and 3 is really obvious, because you could just use the inverse for P or for Q. So here I'll write that. So there's nothing really to say there. But how do we connect the existence of these things to everything else? And how do we connect that to it being actually invertible? Like, it's hard to go back the other way from these, because if you just know there's an inverse on one side or the other, it's actually really hard to show that that works on the other side, because in general, matrix multiplication is not usually commutative. You don't know that QA is going to be the same thing as AQ. So the thing you need to do is to connect thing 2 to thing 6. And you're actually going to do that as an exercise. It's one of the exercises in section 2.2 or 2.3, I believe. And it's actually the same thing that 3 implies 8. That if there exists a Q, so that A times Q equals the identity, that implies that AX equals Y always has a solution. So you're going to do that bit. All right. What we have left to do is, I think, the trickiest part, which is showing that if A is row equivalent to the identity, then that means that A is invertible. Oh, but wait, we haven't done the if A is invertible, then A is row equivalent to the identity yet. That is true because of theorem, what number was it in 2.3? If A is invertible, then this augmented matrix, A augmented with I, is row equivalent to I augmented with A inverse. And if this is true, then the A part must be row equivalent to the I part of this, right? So that is theorem 2.10. But yeah, the hard part is that if A is row equivalent to the identity, then A is invertible. And the trick to this is elementary matrices. We'll see how it works more rigorously, but just to sort of give you an idea of where we're going with it, if A is row equivalent to the identity matrix, there exists a sequence of row operations that all have elementary matrices that represent those row operations, and you can represent that as matrix multiplication. And that's what invertibility means, is that there's a matrix you can multiply to get the identity. So let's work out the details here. So we start by assuming that A is row equivalent to the identity. And we want to show A is invertible, which means A inverse exists. Now, if A is row equivalent to the identity, there's a sequence of row operations that reduce A to the identity, and each of those corresponds with an elementary matrix. And we know that multiplying A by these elementary matrices on the left will do that row operation to A. So in other words, we can say A is row equivalent to E1 times A. So that's like the first operation in the sequence of operations. And E1 times A is the result of doing this row operation to A. And we could keep doing these row operations. And here's the result of doing the second operation after doing the first operation to A. And we keep doing this until we get the result of n of the operations. I don't know how many there are. And they're all multiplied in the right order by A. And we know that is going to be equal to the identity. Now, I mean, we're kind of almost there, right? You can see we have something multiplied by A to get the identity. Well, that doesn't necessarily mean that if we change the order of these, it would still work. So we still have a bit of work to do. So we know that elementary matrices are always invertible. We talked about why that is before. And if each elementary matrix is invertible, the product of invertible matrices, which is this whole thing, is invertible as well. And that's from a theorem also in 2.3 here. Yeah, if like instead of A and B, we have these elementary matrices, so the inverse exists, and we can multiply by it. So here we're multiplying both sides of this equation here by this inverse of these elementary matrices. And we know we can move parentheses around. We got associative rules, so that will cancel out and give you just the identity times A equals this thing times I, and the times I doesn't change it on the right either. Or in other words, this just says A, because the identity on the left doesn't change anything. A is just equal to this. Okay, so A is the inverse of an invertible matrix. What does this theorem here say? Well, instead of A here, I want to think of this A as that product of elementary matrices. The inverse of a matrix is invertible as well, is what this says. So the inverse of an invertible matrix is invertible as well. Which is what we wanted to show. We wanted to show that A is invertible. And that is the last piece of the puzzle here. And the invertible matrix theorem is proved, and now you can use it to make all kinds of conclusions about all kinds of stuff. You've got some homework problems where you gotta just practice using this. You've got some other assignments where you're working with elementary matrices to get some practice with that. I think elementary matrices, by the way, are interesting not just because we use them for this proof, but I feel like elementary matrices help you understand what's going on in this rich, complicated process of multiplying matrices together. Like there's all the different ways you could write a matrix times another matrix as we saw here. And elementary matrices gave us a good excuse to see different ways that you can think of matrix multiplication. And of course, it also helps us make a connection between matrix multiplication and row equivalence and doing row operations, which we needed for this proof. And we're also going to use elementary matrices in chapter 3 a little bit later, so they're not going away. Neither is this theorem. So anyway, good luck with the homework, and I will see you next time.